So this is going to be a video on digital logic, and what I hope to do in this video is teach you how your computer would actually add numbers, right? And so I'll be showing you how to build out a portion of your arithmetic logic unit. And what you're actually looking at here is a working CPU built out in Logisim, from logic gates all the way up, right? And this software I'm using here, well, it's called Logisim. If you'd like to follow along with this video, I highly recommend you download it, right? So let me just give you an idea of what this might look like. Set the frequency much higher. There we go. So it's a working CPU pretty much. And this kind of project, it's quite involved. I think it'll take you a while to build something like this yourself, but I hope to at least give you a glimpse of how you might start doing something like this. And it's really not as difficult as you might think, really, especially if you can find the right resources to teach you. But alright, I'll be going over the what's called a full adder, right? We'll be building a full adder. I think the proper name for it is a ripple counter or something, but it's essentially how your computer would add numbers together. And so we'll be building pretty much a simple calculator, right? And okay, let's just get straight into it then. Let me just quit here. Let's open up another instance of Logisim. Great. Oh, not great. One of the many caveats to this desktop environment. I do like it, but sometimes it gets a bit annoying. You kind of have to wait for the applications to load entirely. Okay, and I think we're good to go. And really what I'm aiming to get across here is to give you a first principles understanding of how you can actually build these circuits for yourself. Sure, you can go online, you can look up the circuit diagrams and you can just sort of copy them for yourselves, but I don't think that's really giving you a proper appreciation or understanding of what you're doing. And more importantly, right, you don't have any skills that you can go and look at some novel problem and solve for yourself. And so what I'll attempt to do is show you how I might approach a problem like this and solve it, you know, from the ground up, pretty much, right? And then you can approach any other problem. Obviously, there are many different ways of problem solving, but I just hope to give you a glimpse of what that might look like. So, okay, let's assume we wanted to add two binary numbers, right? How would we do this? Well, let's say we wanted to add 0, 1 and 0, 1, right? And here's where I'm hoping you have a little bit of discrete math background, because I don't want to spend too much time building up on prerequisite information. You can find that online quite easily. So 1 and 1 would give you 0, right? And there's a carry of 1, and then you bring that down. So this is the binary number 1 plus the binary number 1 would give you the binary number 2, right? 1, 0 is 2. Okay, that's pretty straightforward, right? How would we build a circuit to do something like this, first of all? Well, you should know, right, that every circuit is more or less, not more or less, it is fully described by a truth table, right? So that's a pretty strong hint of where you can start. So let's start with a truth table and try to describe the behavior that we're seeing. So we know, right? And whenever you have a truth table, all you need to know is, what are my inputs? What are my outputs? It's the only question you need to ask yourself, okay? You don't need to ask yourself anything else. So let's look at this problem again and ask ourselves, what are the inputs? Well, this was an input and this was an input, right? So we had two inputs. So we had A and we had B, right? And then what did we have as an output? Well, we had the 0 here as a sum, right? So we had our result there. And then we had a carry, right? Something carried over here. So we had a carry. So we've got two inputs and we've got two outputs, okay? And you should know then that this would just be 2 to the second, right? To cover all possibilities. So 1, 1, 0, 0, 1, 0, 1, 0. Okay, and then you just fill out the table, right? So 1 and 1 is 0, as we just saw here, with a carry of 1. 1 and 0 would be 1. no carry. Same thing here, no carry. And then there's nothing here. Great, so we've got our truth table. Now comes an important thing that you need to know. It's called sum of products, right? And this is how you're going to be able to describe your truth table, right? And construct a digital circuit out of it. So how sum of products works, right, is sum, right, means an OR gate. Every time you see the word sum, think of an OR gate. And when you see the word product, think of an AND gate, right? So it's a sum of products. So you have a bunch of AND gates, right? And they're all ORed together, essentially. So how does this work, pretty much? Let's take an example here. And you're only looking at the outputs, right? And it's a form of retrograde analysis, wherein you're looking at the output state and you're trying to work backwards, right, to some initial state that led you to that output state, okay? So let's look at our output cases. We don't care when the output is 0. We only care when it's 1, right? So we'd start here, for instance. And let's draw our AND gate. Suppose we had an AND gate like so, right? And we know in this case, right, that A is 1, right? So we can just give it A. And then B is 0, but we can't give it B, right? Because B is 0, and 0 and 1 would result in 0, which is not true. In this case, we're expecting a 1, right? So what you do is you invert, right? You invert B. You say not B. Okay? I hope you understand what's going on here. So every single time you see a 0 in your input case, you invert it so that the output case becomes true. Okay? That's how you describe your circuit. So let me just show you this in example, and hopefully it becomes clearer from there. So we'd say S, right, is equal to, and then you come here to the first case, A, as we just saw, right? A and not B. Remember the AND, right, represents, or the product rather, represents an AND gate, right? So the product here, A and B, and then we add, right, OR gate, and then we come to the next case here, which is over here, which is just not A and B, right? Not A, we invert to 0, and we give it B. So not A and B. Okay, and so it's a sum, quite literally a sum of products. All right, and then we come to the other output here, which is C. We say C is equal to, and then we come up, so 0, 0, 0, we don't care about that. It's only 1 in this first instance here, and it's already A and B, right? We don't have to invert anything, right? So we just say A and B, like so. And this expression here actually describes our entire circuit, believe it or not. And if you're a bit more advanced, you can already look at this truth table, and you might recognize that this is the exclusive OR gate, right? But I'm not assuming you know any of this stuff. I'm trying to teach you from the ground up how you might go about reasoning these problems for yourself, even if you don't have sort of a lot of prior knowledge, you know, built up for yourself. But it's good to know the exclusive OR gate will simplify a lot of things for you, but you don't have to know it, okay? And, alright, we're just using the primitive logic gates, as it were. So first principles understanding of what's actually going on here. So let's get into this software, and I'll try to teach you how the software goes along the way as well. So let's start off with the input, right? So this is an input pin. Let me make this a bit larger. This is the input pin, right? This one here is an input pin. So we know we need two inputs, right? We need an input A, and we need an input B. Great. There's also something else we need. We need our input to be inverted, right? Because we know we're also going to be taking not A and not B. So let's just go ahead and invert that as well. So we got the input covered, more or less. So the first thing we're looking at here, the first gate, right? It's an AND gate, so it's A and not B, right? So let's pick up an AND gate here. So it's A, right? So let's grab A, and it's not B, so let's grab not B. Great. And then we come to this plus sign here, which I already said denotes an OR, right? So it's an OR gate. So that's feeding into an OR gate, right? And then we come over here now and we say not A and B, right? So not A, so it's another AND gate. Oops. Here it is. So not A, let's grab not A from up here. And let's grab B from right here. And this feeds into our OR gate like so, right? And this produces an output here. This one here on the right side is the output pin. And you can double click to label it, so we'll say S for sum, right? Great. And then now, so we've already described S, and it was as simple as that, by the way. And then now we have to describe C, right, which is just A and B. So we can say get another AND gate here, maybe, and it's just A and B. So we'll grab A from up here. Oops. Put this here, and we'll just pick B from right here. Grab another output pin, and we'll say C. And now let's go ahead and test this to ensure it actually works, right? So we know when we add 0 and 0, the sum would be 0, the carry would be 0. When we add 1 and 0, the sum is 1, the carry is 0, right? We can do it the other way as well, right? Same thing, sum is 1, carry is 0. But when we add 1 and 1, the sum is 0 and the carry is 1. Can you see that this circuit pretty much describes our truth table that we built out, right? And this contraption, if you want to call it that, is called a half adder, right? And so now I'm going to introduce you to something in computer science you'll probably hear a lot, especially in computer architecture. We're going up a level of abstraction now, right? So every single time I need to use a half adder, I don't want to have to build this circuit out again and again and again, right? And then it's gonna become extremely complicated as well. So you really want to abstract these things away. How you do that is come over here to project, right? Say add circuit, and we'll say half adder, like so, right? By the way, a fun project to do on your own as well after you finish watching this video, if you like, just go online, order some transistors, right? And do some research, and you can see that you can build logic gates from transistors, right? And I just show you that entire CPU we built out with logic gates, right? And so then it logically follows that if you had transistors, you can build a CPU, right? Which is quite literally what your modern CPUs are. It's just a bunch of transistors arranged into logic gates, right? To build up this wonderful piece of machinery that you're using. So, but for a simple project, you can just build a half adder or build the full adder if you want, and play around with it that way. I think you learn a lot. But okay. We created our half adder here, so let's go back into main. Let's copy everything here. Let's copy the selection, and let's paste it here into our half adder. Let's come on back here, let's get rid of this, and then what you can do is bring your half adder in like so. Okay, and we can test that it works exactly as we would expect, right? So let's just put in some new input pins here, A and B, right? And let's put our output pins. So that's the sum, and this one's for the carry. Great. And okay, 1 and 0 is going to give you 1 as you expect, and same thing for the other way, and then 1 and 1 would give you 0 and 1. Functions exactly as you would expect, but now you don't have to look or think about the entire circuitry. You know it, right? But you don't have to think about it. You can abstract it away. Okay, so let's get back to our example here. Insert page after. Yeah, that should be fine. Alright, great. So let's suppose now we wanted to do this. 1, 1, 1, 1, right? Suppose we wanted to do this now. What's going to happen? Well, we know 1 and 1 is going to give us 0 and a carry of 1, right? So we already have something that's capable of carrying out this first operation here. It's our half adder, right? Our half adder is going to carry out this first. It's going to take two inputs, right? Produce a sum, and it's going to produce a carry. Now, the half adder, we can't reuse it, right? Because if you look here carefully, we're expecting 3 inputs now. There's a carry as an input, there's A, and then there's B, right? The half adder simply isn't designed to accept 3 inputs. So this is where we need another piece of circuitry called a full adder. And we're going to derive the full adder the same way that we just looked at our half adder, okay? And so we say, okay, what are our inputs? What are our outputs, right? And so, by the way, let's just carry out this. You should know that 1 plus 1 plus 1 would give us just 1, right? With a carry of 1. I hope you know that, by the way. Okay, so 0, 1. Oops. 1, 1. So if you were to look at this binary number here, this is the number 3, right, in binary. Okay, so it produced a 1 here, right, and the carry, and then it carried another 1 over. Okay, I hope that makes sense. So 1 plus 1 plus 1 would give you 1 and a carry of 1. Again, if that didn't make any sense to you, I think you need to do a bit of brushing up on binary, okay? Before you come back to this video, for you to really understand what's going on. But okay, so we know we need a 1 here and a carry here, right? And then this would just come down like so. But okay, let's go ahead and focus on this second step here that we were working towards, right? So how would we do that? So we ask ourselves a very simple question again: how many inputs do we have? How many outputs do we have? So we know we have 3 inputs, right? We have the carry, we have A, and we have B. So we have A here, we have B here, and we have the carry as well. How many outputs do we have now? Well, there's a sum, as per usual, right? And then this also produced the carry, right? So there's also the carry that we need to consider as well. Okay, and then you should know 2 to the third would give you 8, right? So I'm going to use red now. So 1, 2, 3, 4. 1, 2, 3, and 4. I'll need to drag these down a bit. Okay, it's going to take a while, but we'll get there. And then, okay, and I hope this pattern is starting to become obvious to you as well. Then we just half it, right? 1, 1, 0, 0, 1, 1, 0, 0. Then you half it again, 1, 0, 1, 0, 1, 0, 1, 0. Now, if you haven't seen this before, I'll show it to you now, and hopefully it'll make sense to you. Why is this covering? How are we certain that this covers all possibilities, right? Well, if you look very carefully, look at the bottom here. This is the number 0 in binary, right? And then this is 1, right? And this is 2, and this is 3, and this is 4, and this is 5, and this is 6, and this is 7, right? Okay, so 0 to 7, 8 possible combinations, right? 2 to the third is 8, covers all possibilities. Okay, so that's a pretty neat something if you never saw that pattern for yourself before. But okay, let's just go ahead and fill out this table and then make our sum of products and construct our full adder. So 1 plus 1 plus 1, as we already established, it's just 1 and 1, right? Sum of 1, carry of 1. 1 plus 1, well, 0, and the carry of 1, right? And then 1 plus 1 again, right? 0, and the carry of 1. Then, okay, just a 1 here, no carry. Then 1 plus 1, 0, carry of 1. 1 here, no carry. 1 here, no carry, and then there's just nothing here. And remember, we're only interested in the cases where in the output we had a 1, right? Where something evaluated true in the output. Okay, we don't care where it's 0. So we see that we have 1, 2, 3, 4 expressions we need here on the sum side, and then the carry we also need 4 expressions as well. Okay, so insert page after, and then so we can go ahead and start from the very beginning, right? So let's start with this first case where we had an output here. So we'll say S is equal to, right? Well, A, B, and C, which is already 1, 1, and 1, so we don't have to do anything there. We just say A, B, and C. Okay, that's our first expression. And then we add, right, something else now, or together with this next one here, which is A, and then there's 2 zeros here, so we need to invert these. So it's going to be A, not B, and not C, right? So A, not B, not C, like so. Then we add it with something else now. So we're on to the third one. Well, we have B here, right? So it's not A, not C, and just regular old B. So not A. Let me double check that. Not A, B, and not C, right? Then add it again now with something else, the last case, which is not A, not B, and C. So not A, not B, and C. Great, so this describes what we're going to need for the sum portion of our output. Now we need the carry, right, the next output. And here, same thing, A, B, and C. A, B, and C. And then down here, we're going to need A, B, and not C. You can see this is getting quite laborious as it is. And then we have A, C, and not B, right? A, C, and not B. Then finally now, we've got not A, B, and C, okay? Not A, B, and C. By the way, these circuits that I'm showing you, not optimized. You can build these in a better fashion, right? But I'm not doing that. I'm trying to show you how you can reason this out from primitive gates all the way up, okay? Obviously, these expressions, right, you can minimize them, right, to make them more efficient. But as is, for now, we're not doing that. Okay, trying to keep this as simple as possible for you guys. Okay, so let's go ahead and build these out, right? So what we're gonna do is we're gonna go over here to project, we're gonna add a new circuit, we're gonna call this one full adder, right? We're gonna come over here to our full adder and we're gonna start building. So the first thing we need is an AND gate here, right? But we have 3 inputs now, okay? So what you're gonna do is select your AND gate, where is it? Here. Click on it and you see here number of inputs is 2, we need this to be 3, so change it to 3. Right, so now it's accepting 3 inputs, so we're good. And let's get our input pins, and we need 3 input pins, so 1, 2, and 3. And let's label them. So this one's A, this one's B, and this is our carry input here. Great. And let's do the same thing as we did the last time. Let's set up our lines and invert them at the same time. Okay, and I think the first one was just A, B, and C, right? Yeah, so we don't have to do anything too fancy there. What's going on? Oh, here it is. So just A, B, and C, right? Pretty simple stuff. And then we have the plus sign, which means an OR gate, right? OR together with our next expression, which is A, B, oops, we're up here. A, not B, and not C, right? So let's get our AND gate again. Let me just delete this. I can just copy this. So it was A, not B, and not C, if I'm not mistaken. Yep. A, and then we come here, we're going to grab not B. It's kind of far off, but okay. We're going to grab not B. And then we're going to grab not C as well. Right, these two are ORed together. Great, and then, right, another plus sign, which is another OR gate. So we get another OR gate. Where is it? Here, right? And then this is what we're dealing with now: A, B, and not C. So let's get another one. So I think it was A, B, and not C. This is A. This one's B. And I think not C is here, right? So we can just borrow this line right here. Okay. Now we're here, right? So another OR gate again. Every time you see the plus sign, it's an OR gate, right? So the entire expression is just sort of compounding as you go. So a bunch of sum of products, literally. Okay, and so oh wait, I think it was not A, B, and not C for this one, so I made a mistake there. You have to be careful with these things. So it was not A, so that was my bad. Delete this. It was not A, so we'll have to borrow from here. Right, so not A, B, not C, and then not A, not B, and C comes here. So not A, I'll collect it from right here. Not B, I'll borrow this from here as well. And I think it was just regular low C. Not A, not B, and C. So let's get C from here. Obviously this is just very, very ugly circuitry. I'm not really concerned with that though, because I'll be abstracting it away, so it doesn't have to be the previous circuit, right? And we're going to put in our output pin here. So this is going to be our sum now, right? Sum, and we're going to need the next one now. So we're finished with the sum. Now we have to build the carry. So it's going to be the same thing, A, B, and C again. Right? So we're going to build the carry at the bottom here. So we're going to need A, collect this from here, B, and Whoops, that was a mistake. I'll just drag a new line. And C. Right, and that's OR together with, let's see, A, B, and not C. So just collect the A from here. A, B, and not C, which I'm going to have to get from here. No, it's here. I'll just drag this line out and bring it around here. And that's the second one, and then that's OR together, right? OR together with this, A, not B, and C. So A, not B, and C. So let's get A here. Not B, which is here. Just drag it all the way around. A, not B, and was it C? No. It's, yeah, A, not B, and C. Yep. Where's the C? I'll just collect it from right here. There we go. And put this in here. Then it's OR together again now. Right? We're getting there. So it's not A, B, and C. So let's get another one. So not A, we'll just grab it from up here. Whoops, did not mean to do that. Not A, B, so we'll get B from here, I think this one's B, right? We can follow it down here. Not A, B, and then what do we need? C? Yeah. So we'll just come all the way up and collect from C here. That should be it. Hopefully I didn't make any mistakes. It's quite easy to make mistakes, especially when you're doing it a bit carelessly like I am. But I'm going to count on our years of experience to carry this through. Okay, so let's test that this circuit functions as the truth table described, right? So obviously we know 0, 0, and 0. We're not going to get anything here, right? Then 1 plus 0, all right, plus 0 should give us a 1 with no carry, right? And then 1 plus 1 should give us 0, right, with a carry. And then 1 plus 1 plus 1 should give us a sum of 1 and a carry of 1 as well. There we go. Okay, so the circuit functions just as we would expect, and this is our full adder, okay? So hopefully that's clear how we went about doing that. So let's go back to our little drawing now. Okay, I'll use blue now. So let's go back. 1 plus 1 plus 1 plus 1. This is our contrived example here. So we know, right, in the first instance, we used the half adder circuit, right? We used the half adder here, right? So if you can imagine, we have our half adder circuit here. And we gave it input A, we gave it input B, and it gave us the sum, and it gave us the carry, right? So 1 plus 1 is what? 0, right? And so the sum was 0, and it gave us a carry of 1, right? So this came up here. And now we decided we need a new piece of circuitry, pretty much, to go ahead and carry out this input for us, right? Or this computation for us, because the half adder simply wasn't able to do it. So we came up with our full adder circuit now. So our full adder circuit is going to take in 3 inputs. It's going to take the carry, right? And then it's going to take your regular A and B inputs, pretty much, right? And so the carry, though, is coming from the output of the half adder, okay? So this output here is feeding into the carry of the full adder, in addition to this. So we've got our full adder here now that we just built, and the full adder is going to produce a sum and a carry as well, right? And we know the full adder is going to give us a 1 here, right? And then it's going to give us a carry of 1 as well, all right? Give us a carry of 1, and That's going to come down here. And if you can imagine, we had a 0 and a 0 here as well, right? We can feed this into another full adder, right? Which would just add 0 to 0 and the 1 to give us the correct output. So let's go ahead and build our 8-bit adder, right? And this is literally how your computer adds numbers, by the way. That's how your CPU adds numbers. So we have the half adder, right? This is where we're starting at. And then we need a full adder, as we said before. Let me go ahead and delete this. Delete this. Oh, I do need the sum, though. So, yeah, we'll keep the sum, but we need to delete this. So we said before that the half adder's output right here is going to feed into the carry, right? This carry is feeding into this carry, and then we need A and B again, okay? We need the two numbers here that we're adding. So let me put in some input pins here. Put pin here, and another input pin here. Okay. And I didn't label, let me go back to the half adder, or the full adder rather. I didn't label this, so I'll call it carry. And full carry, to be a bit more descriptive. Yeah. Go back to main, there we go. And we're going to need to output our sum, obviously. So, I'm gonna put this like so. Great. And then now I can go ahead and just copy this. Copy, paste, right? And so we're going to do it 8 times, right? Or 7 more times. So we're going to build an 8-bit adder, right? So we can handle up to 8 bits of data, pretty much. Oops. Again, so we know that the carry feeds in here, like so. Then we'll just copy this. Right? And again, we know the carry is going to feed in, like so. So we've got, let's copy it again. We've got 1, 2, 3, 4. We're going to need 3 more. So we're going to copy. I'm just going to copy these 3, like so. And then the carry will feed in like so. And the sum didn't come out for some reason, so I'll have to put this in. And then we have a carry here as well, which we're going to do as the output. We're going to call this overflow, by the way. So if there's an overflow, right, this means that the digit that we're trying to add can't be represented by simply by 8 bits, right? You're adding something that's too large. And you would just have to keep expanding this outwards, by the way. And so your 64-bit computer or your 32-bit computer simply just has like 32 of these, right? Or 64 of these is stacked next to each other. And so that's the number, the largest number that it can pretty much compute, right? So yeah. Hope you're getting an idea of how your computer architecture might start to be organized. So this is just for an 8-bit CPU, right? So if you wanted it to be 64, then you'd need, well, 64 of these, right? But we've only got 8 of them now. Well, actually, it'd just be 7 of your half adder, 7 of your full adders rather, and 1 of your half adder, okay? With this particular system. So for a 64-bit system, 1 half adder and 63 full adders, which I am definitely not going to do here because that is too laborious to do. Okay. So let's go ahead and label these inputs now. I think it's pretty important, and then we'll test that it works, okay? So I've got to come up with a way. So this is obviously the ones column, right? So we'll say ones A. Instead of ones, we'll say 1A, 1B, right? I should stick consistently, so. And then we'll say 1 sum. Oops, can't do that really. 1 sum. Why isn't it? I think my keyboard might have a, yeah. Okay, and let's label this one 2, 2A, 2B, let's say 2 sum, then 3A, 3B, 3 sum, Actually, it's gonna be 4, right, if we're doing this. 4A. Because it doubles. 4B. 4 sum, and then 8A, 8B, and so on and so forth, right? And we're just gonna go all the way down. Okay. Then it's 16. 16A. 16B. And then it's 32. Can I use numbers? No, I can't. Okay, I'm just gonna say TT, TTA. No, I need to be descriptive. 32A, yeah. 32B, 32 sum, then 64, 64A, 64B, 64 sum, 64, well, this is 124, so 124A, 124B, and finally, well, it's not connected here. Okay. 124 sum. Okay, that was very, very, very involved, but I think we have everything we need to do now. So let's go ahead with our little example we were saying before, right? With just 1, 1, 1, 1, right? So here, okay, if you look at this very carefully, on the half adder, the input would be A, and so A would be 1 and B would be 1, right? So let's set this to 1 and 1, right? And then over here now, the input on this side inside of the 2's columns here would be 1 and 1 as well, right? So 1 and 1. And if you look at the output, it's 0, 1, 1, okay? Which is exactly what you would expect. So if there was a 0 here, and you can imagine the zeros are just trailing. Yeah, so it's exactly as you would expect. So you have to read your answer now from this way coming up, okay? So you read from this way up. So it's 1, 1, 0, okay? So a whole bunch of zeros, right? A whole bunch of zeros, so you reach 1, 1, and 0. So that's your correct answer, 1, 1, 0. Alright then, so now we can go ahead and actually abstract this away. That circuit, so we'll say full adder. No, we don't need something else. We'll just say ALU add for now. And then we'll come over to main, and we'll copy everything. Come on, there we go. Copy selection, come back to here. And we'll paste it in. So then we can come back to main now. Let me zoom out so it'll be easier on me. We delete everything here. Delete all of this. And just grab our full adder. That's our full adder. Yep, very, very ugly looking, but we'll make this better. Okay, so this is our full adder. So come over here to, I think it's input or wiring. Where is it? It has to be input. Input output, right? Grab the, what is it called? The dip switch, right? Grab the dip switch. So we'll use a dip switch. Get 2 of them, right? And so if you can imagine, we're doing our addition like this. We're gonna say the first dip switch is going to represent like the first row of numbers that we're adding, and the second dip switch is going to be the second row of numbers that we're adding together, right? And so this would go to 1A, right? This would go to 1B, right? This one would go to 2A. This is 2A's input. I hope this makes sense to you. This goes to 2B. Then this one is going to go to 4A. Oops. This one's going to go to 4B. I should drag this thing a bit more and get some space. This one's going to go to 4B, and then this one is 8A, right? This one's in the 8th place, then, as it were. Then 8B. Then we just do this for all of them, pretty much. My mouse is malfunctioning. And then we go over to 16. Do the same thing here. Oops. You gotta be careful with these wires not to have them intersect really with anything else. 16B, and then 32 now. Whoop, keep intersecting. I'll bring it all the way up. Or I'll just take it around. I don't have to do it, I'll just bring it down, give some more space. So 32B and then 64. B, and then finally 124. It's supposed to be 128 actually, not 124, so that was my bad there. So let's go back into our full adder, or ALU add rather, and we'll say, we'll rename this to 128A and 128B. This is going to be 128 sum. There we go. That should be fine now. Just go back to main, and it's fixed. Okay, and then now we need a way to obviously output the result. So we're just gonna use some LEDs here. Yeah, I'm gonna use some good old LEDs, and we're gonna start from the least significant bit, right? So we're going to start with the 1. Let me copy this a couple of times. Great, so we've got 8 of them, like so. So we're just going to be able to literally read off the digit, pretty much, right? So that's going to be for the 1 columns. This is going to be the sum for the 2 columns. For the 4 columns, 16, 64, 128. I left that one. So this one's 4. This one's for 8. This one's for 16. This one's for 32. Okay, and so on and so forth. And then finally we've got 128. And then this is the overflow. So if this is on, it pretty much means that we can't display that value, it's too large, okay? That means there's an overflow. You need more full adders, pretty much. So let's try some additions, right? So 1 and 0, what are we going to get? 1 and 0 is 1, right? 1 plus 1 is 2, right? And then let's say now we wanted to add 128, right? 128 plus 1. There we go, 129, right? Just as you'd expect. Let's say we wanted to add 64, right? And 64. Oops. 128, right? Just as you'd expect. And then let's add 1 again. So then 129 now. 129, there. Just as you'd expect. Now let's try to add a number that's just way too large. So let's see, let's add this, and then this. Just turn them all on. Yeah. Alright, so this is obviously the largest number that we can hold, right? It's 128 plus 64 plus 32, 16, 8, 4, 2, and 1. Whatever that number is, right? You can do the computation there. That's the largest digit that we can represent, right? And so this is actually how you would know. Let's actually do that calculation, to be honest with you. Let's do that calculation. So let me get out my calculator. So 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. It's 255, right? So, oh yeah, that makes sense to you, right? We didn't even have to, but okay. Yeah, that makes sense. So it's 255. And you should know, by the way, that for instance, if you're storing values, you should know that 8 bits is 1 byte, right? And if you're familiar with C programming, which I think many of you, if you're in college, you've been doing quite a bit of C programming as well, you should know that a character is represented in memory as a single byte. So inside of your computer's memory, right, it's literally 8 bits stacked together like this, and we'll do memory later on, and you'll see how memory actually is built out with logic gates as well, and how it's stored in your computer. But if you can imagine, like, this was your memory, right, and you had a byte, 8 bits, right, 1 byte, then it's 255, right? And if you know, right, that you can, that's the range that you can select values from, it's up to 255, okay? So, and obviously that's for signed integers. So there's signed and there's unsigned as well, but we won't get into that right now. But what I was trying to show you at first is what happens when you try to add something else now. It's going to overflow, right? It's going to overflow. So actually what's happening here is this is going to be 256, right? This, if this was here, and then just everything else there, right? And then if you try to add more values in, then obviously it won't give us an accurate representation because it's simply just overflowing at this point, right? Okay, so information is being lost in the system in that particular case. And so if you know you need more information, then you can go for signed or unsigned integer and things like that, so you get more space on the computer. Alright, so yeah, that should more or less wrap up what I was hoping to teach in this short, well, I was hoping to be short, but it turned out much longer than I expected. It's just so laborious, right? But yeah, there it is. That's how your computer adds numbers in binary. So yeah, have a good one.